Hello everyone. In this video, I'm going to discuss a topic that many undergrad students find difficult to understand in their general physics course. This topic is the free body diagram of a body of mass m moving inside of a vertical circle as is shown over here. This mass is moving with uniform speed v and therefore uniform angular speed omega in the clockwise direction. Of course, it does not have to be a clockwise direction, but we'll just go with the clockwise direction here. The question is to find the free body diagram at the top and at the bottom of this vertical circle. So let us start with the top of the circle and find all the forces acting on the mass m. So there will be two forces here. Let me put another page over here. So I have drawn over here just a circle, two circles over here, and I have shown the mass in this circle at the top and the mass over here in this circle at the bottom. And we want to find the forces acting on the mass to to draw the free body diagram. So there will be two forces here, right? One will be the gravitational force and the other will be the normal force. The gravitational force will of course be pointing downwards. So this will be the gravitational force Fg, and of course Fg is nothing but m times g, the mass times acceleration due to gravity. Um, it is the normal force that creates a little bit of confusion in students' minds. Some students wrongly show its direction to be pointing up when it is at the top of the circle. So this sort of end up with something like this, right? But this is wrong. That is not how it is when the body is at the top of the circle. This confusion, stems from the fact that when they study general physics, they deal with some situations where they come across, for the free body diagrams where they show the forces. The gravitational force would be, of course, pointing down, but the normal force would be pointing up. So, for example, if they come across a situation where the body is moving on flat surface and it's moving in this direction, the gravitational force they have no problem with, but the normal force, they do it like this, which is correct in this situation, but it's not correct in this situation. So this is not how the normal force is going to look like, and it's clearly not the same situation as this situation over here. The body is moving inside the circle. So what happens over here at the top, it's pushing up against the wall of the circle. So the way to realize this and not make a mistake ever again is to think that the body is not quite at the top of the circle for now, but it's about to reach the top of the circle. All right, so it's just like, a small moment, a little moment before it is about to reach the top of the circle. So what I have used over here, I'm using an earplug over here. So for example, this earplug is moving around the circle like this, right? So what happens over here is that a body, when it's moving inside the circle, is going to have a tangential velocity which is pointing outwards. So something like this, right? It's going to have a tangential velocity which is pointing outwards like this. So at every point, the velocity v is going to be pointing tangentially outwards. Now a body has mass, and mass has inertia, and inertia does not like the change in the motion. So if it's going straight, it likes to go straight. It does not like to bend around like this. So it's the walls of the circle that are making the body bend around, uh, uh, and move it inside the circle like this. So what happens that as the body is about to reach the top of the circle. All right. So let's think of a moment when it's right here, right? Just a moment before it's about to reach the top of the circle. So what happens in this scenario is that when the body, its tangential velocity is going to be pointing out this way, so it wants to go out that way, but the walls are preventing it from going there. So what happens is that, imagine that my hand that I'm putting over here is the wall of the circle, and the body is inside the circle like this and moving inside the circle. So right when when it reaches the top, it sort of pushes up against the circle like this, right? And the walls are preventing it from going out, so the walls are pushing it downwards like this. So the reaction force, right, so it pushes it like this, right, just when it reaches the top, and the reaction force from the circle is going to push it downwards like this. So right when it reaches the top, the reaction force is also pointing downwards and not upwards like this. Never mind the different sizes of the arrows. I'm just showing that to differentiate between both of the forces. So this is what happens when the body is at the top of the circle, and we can apply the same logic when the body is at the bottom of the circle, right? Mass at the bottom of the circle. So again, the same scenario, the body is moving like this. So just a moment before it is about to reach the bottom of the circle is right over here. And in this scenario, the tangential velocity will be like this. All right. However, now, just when it reaches the circle, it gets a little awkward with my hand over here, but you can imagine again that the walls of the circle are like this, and the body, when it reaches the bottom, when it reaches the bottom, is going to push against the walls of the circle, right? It was a little awkward to put my hand over there, but you can imagine that it's going to push the walls of the circle, and the walls of a circle are going to react back and sort of prevent it from moving it in this direction. So the reaction force in this case will be pointing inwards. And of course, gravity, as before, is always pointing downwards like this. All right. And that is how these are the two free body diagrams of the body of mass m moving inside of a vertical circle, one's at the top and the other at the bottom of the circle. And once you have this free body diagrams, you can very straightforward write down the Newton's laws. This is a scenario where we are going to deal with a centripetal force. So another mistake that people make is they have to realize that the centripetal force is sort of not a force, as in it's not a physical force in the sense that the mv square over r, the centripetal force, this is sort of not an actual force in the sense that there has to be some physical forces which play the role of a centripetal force. So mv square over r, this equation, this formula by itself is not the centripetal force. Some force, a physical force, an actual physical force, plays the role of a centripetal force. So in this scenario, the way we will write it is, first of all, we'll choose a coordinate system, just for because force is a vector, and we need direction for our vectors. So this will be the positive y-axis, this will be the positive x-axis. So any forces pointing up will be considered with a plus sign, any forces with a pointing right will be considered with a in the x direction will be with a plus sign. Of course, there are no forces over here at the top and the bottom, at least, where they are in the positive x direction. Only the y forces are present over here. So clearly, these two forces are pointing in the negative y direction. So we'll put minus f sub n, then minus f sub g, and that is equal to minus mv square over r. Therefore, f sub m minus mg equals minus mv square over r. And therefore, you get your final result that f sub m plus mg equals mv square divided by r. And this clearly makes sense over here because both of the forces are pointing downwards, so they are going to add up, and both of them combined, the effect of both of them combined is going to play the role of the centripetal force, which is going to be pointing inwards towards the center of the circle. Similarly, in this scenario, you can see that one of the forces is pointing up while the other is pointing down. So you have your Newton's laws over here as F sub m with a plus sign here minus F sub g. And the centripetal force is going to be pointing inwards, right? Centripetal force by definition is a centrally pointing force. So it's pointing inwards at the bottom of the circle like this. So it's pointing up, is pointing up. So you have mv square over r, and therefore you have f sub m minus mg equals mv square over r. And again, this sort of makes sense once again because you can see that the centripetal force is pointing inwards, and minus mg gives you the centripetal force. So in this scenario, at the bottom of the circle at least, you can say for sure that the normal force is definitely greater than the gravitational force, because the centripetal force, which is the resultant force, is pointing towards the center of the circle. So this was a little video on how to figure out the free body diagram of a mass m moving inside of a vertical circle. So free body diagram at the top and bottom. So thank you for watching my video. If you like my video, leave a like and subscribe to my channel. And if you like more videos, let me know in the comments below. Thank you.